Ladies and gentlemen, welcome to tonight's Studium Generale lecture. My name is Rieneke Verbrugge. I'm a professor of logic and cognition here at the Institute of Artificial Intelligence. Tonight is the third lecture in the series How to Build Your Own Cognition. And this is a series that we would like to give to the community because we exist for 20 years this year. And our mission nowadays is to build continuous cognition. So that's not a robot that you give him a task for today and then you put him in the cupboard overnight and tomorrow you wake him up again. No, we want to make cognitive systems that are continuously learning from the task that they are doing, and they take that knowledge again to their new tasks. And so they have to learn to thrive in dynamic and uncertain environments. And this uncertainty brings us to our speaker of today, Professor Noah Goodman. And as young as Noah Goodman is, he is already one of the world's leading experts in making computational cognitive models of uncertainty. So Professor Noah Goodman studied mathematics and physics, and he finished both cum laude. And then he did a PhD in mathematics, and in fact in low-dimensional topology. And I don't think you will see any low-dimensional topology in his talk today. But it was even more surprising what he did after his PhD. So he went into real estate development in Chicago for a year. But then he decided that that was enough. And then I think he made a very successful decision in an uncertain environment, namely go back into science. So he went to MIT. He was a few years a postdoc there and a researcher. And there he wrote, together with colleagues like Josh Tannenbaum and others, a very influential paper that appeared in Science. And that paper was about growing your own mind. And in fact, that was one of the inspirations of the title of this whole series. So nowadays, Professor Goodman is an assistant professor at Stanford University at cognitive psychology. And at this moment, he has already earned many best paper prizes at different conferences. And he has a McDonnell Fellowship for Cognitive Science, which is a very prestigious fellowship for these 6 years, from 2010 till 2016. So he is an expert in making computational models of very different cognitive processes in language, in decision-making, also in social cognition. And he will speak about all of those today. And I would like to give the floor to Noah Goodman.
So the central question of cognitive science is this one. What is thought? And a big part of the reason that I switched into cognitive science, and I'm extremely happy that I did, is that I can start a lecture with a question that's that big, right? If you study math, you can ask a very particular question, and if you study physics, and certainly if you study real estate. So all cognitive scientists are trying to answer this question in various ways. About 100 years ago, William James gave this answer. He said, "Our mental life, like a bird's life, seems to be made of an alternation of flights and perchings. The rhythm of language expresses this, where every thought is expressed in a sentence, and every sentence closed by a period." And in some sense, my research that I'm going to tell you about today is really trying to understand what those flights look like, the flights from one thought to another. So just to give you a little bit of a flavor of this rhythm of language, as William James called it, imagine that your friend Bob says, "It took 1,000,000 hours to get seated at that restaurant." You interpret that as, Bob didn't like how long it took. It didn't actually take 1,000,000 hours. It might have taken 45 minutes. Imagine Bob says, "I waited an hour." Maybe Bob waited 62 minutes. Maybe he waited 60 minutes. But in contrast, if Bob says, "I waited 62 minutes," he definitely waited 62 minutes. So we'll come back to these examples at the very end of the lecture. But these are kind of to get your appetite whetted for the sort of common sense, everyday leaps of reasoning and cognition that I'm interested in studying. But the way that I want to study them is not just by mapping out the empirical phenomena, what happens, what do people do. It's by trying to explore the principles of cognition. What's a small set of mathematical principles that we can use to actually build cognitive systems on the one hand and understand human cognition on the other hand? So I'm going to motivate 3 different principles, 2 important principles that come together for the framework that I'm going to tell you about tonight. On the one hand, there's an observation, which is that thought is useful in an uncertain world. So even though the world is full of uncertainty, human thinking is extremely useful. It helps us get through our lives and flourish. And this uncertainty comes in a lot of forms. One form is just simply noise. There's a lot of noise in our perceptual and other inputs, and we have to deal with that noise gracefully. A less obvious, but actually much more important form of uncertainty is what's called underspecification. There's not enough information in the world. So imagine that you call your friend on the phone, and before you say anything, he immediately yells at you and hangs up the phone. So you're left wondering, why did he yell at me? Maybe he just wanted to hurt your feelings. Maybe he thought you were a telemarketer. So this is a case where the world gives you one piece of information, your friend's action, and you're trying to recover two different pieces of information, at least two different pieces of information, his beliefs and his desires, in order to explain that. And so there's not enough information in the world, and this is a different kind of uncertainty, which is everywhere in the tasks that humans face. So how can we account for this usefulness of thought despite uncertainty? Well, there's a key principle that's been isolated over the years, centuries really, in cognitive science, which is probabilistic inference. I'll talk more about this as we go along, but if people reason about the world by using the rules of probability, the mathematical rules of probability, that can explain this usefulness because the rules of probability are nothing more than a mathematics that was created for that, reasoning under uncertainty. Okay, so keep this in mind. This is one side of the ring here. There's another observation that leads to a very different principle. The observation that thought is productive. Von Humboldt said, thought makes infinite use of finite means. So what does this mean? Well, imagine that you read a phrase in the newspaper tomorrow, a big green bear who loves chocolate. Probably none of you have ever read or thought about that phrase before, but you can imagine such a thing, no problem, right? There's your big green bear who loves chocolate. You can imagine what that big green bear would do if you encounter him in the national park with a chocolate bar in your back pocket, right? And similarly, there are an infinitude of other thoughts that you could think when you come to need them that you've never thought before and might never think again. This productivity also unfolds over a longer time scale. It unfolds over the time scale of whole cultures that's recapitulated as each child learns about their world. So for instance, the concept of mass and momentum are almost certainly not innate, but we know them. We've learned them and we've constructed them. Or the concepts of nations and cities. Nations, cities, countries, and so on. So we have a huge set of these concepts which are not innate that we've constructed over our lifetimes. And there's a huge, probably infinite set of other concepts that we could still create. So how do you explain this kind of productivity of thought? Well, again, fortunately for us, there's another principle to explain this sort of observation. And that other principle is the notion of compositional representation. So this basically means that if thoughts are built up out of pieces the way that words are built up out of letters, or the way that molecules are built up out of atoms, then you can explain why there can be infinitely many of them, right? We have a small set of basic components and we put them together in various different ways. And the combinatorial explosion lets us explain why there are so many potential thoughts. So we'll come back to this as well. There's one more observation which is kind of in between these two and is going to weave throughout the talk today. And that's the kind of observation or claim that it's actually imagination that drives thinking in some sense. And this kind of imagination you can see in examples like mental visualization. So there's a classic task by Roger Shepard where he asks you to decide which of these shapes is equivalent to each other, and you imagine in your mind rotating them around to see if they match. Or a more real-world situation, imagine that I had a hammer, that this was a hammer, and I threw it through the air. You can imagine what it's going to do, how it's going to fly through the air, rotating, what's going to happen when it hits the wall, and so on. And so this idea is that it's that kind of imagination which is somehow part of our ways of reasoning about the world. And we tag this idea with the notion of a generative model. Basically, our knowledge is knowledge that lets us imagine the ways that the world will unfold in the future in different situations. So my goal in a lot of my research and what I'm going to tell you about today is to unify these three sort of computational principles into a view of how the mind works. And we call that the probabilistic language of thought, hypothesis, It's a hypothesis. So just to summarize that, it's really just restating these three claims. That mental representations, the things that make up our thoughts, are compositional. They're made up like tinker toy structures out of little pieces. That their meaning is probabilistic, and they encode knowledge as generative stories about the ways that things could happen, this imagination that I mentioned. So if these three things are true, this is going to be really useful because the fact that they're probabilistic means that we're going to be able to borrow techniques from probabilistic statistics to do reasoning, to do inference. Okay. The problem is this set of bullet points, it's pretty vague. Right? It's not at all clear that one can actually make a system, a physical system, that actually embodies all of these points, that there's a real thing that you can point to and say, this is an example of this general hypothesis. So what I'm going to show you next is an example of such a system. How would you construct a system that's compositional? So you put the pieces together to build bigger structures. It's probabilistic. You can use it to reason by probabilistic inference and so on. And the key starting point is to focus on the combination of this notion of compositional, you want to put the pieces together, and this notion of telling stories. And to say to yourself, do you know any formal system where you put together pieces, and then they let you essentially tell stories about what's going to happen? You might come up with several things that you're thinking in the back, but I'll forestall that and just say the one I'm thinking of is computer programs. So computer programs are a formal language that we use to tell complex stories about what should happen inside a machine. We say, machine, carry out this complex process, and then the machine hopefully goes and does it. What's striking about computer programs is not only that they're these formal languages for describing what should happen, but that a fairly simple system, a fairly simple computer language, can be universal in the sense that any program, at least any deterministic program, can be written down. So choose your favorite programming language. Maybe you like to write in C or in Java or any other language. It's a universal system. Any program that can be written in any other language, you can write it in some version in your language. So the question is, can we somehow leverage this idea, universal computer programs, to represent probabilistic knowledge, not just the deterministic sequence that you want your computer to go through? So to show you how to do that, I'm first going to take a step back and show you one particular computational system. It was actually the first computational system. It's called lambda calculus. Out of curiosity, how many people in here have heard of lambda calculus before? Oh, that's more than I would expect. Okay, you don't need to have. Lambda calculus turns out to be extremely simple. So lambda calculus is basically a way of making functions and applying functions to arguments, to inputs. So the notation we use looks like this. We might have a function like sine, and we apply it to an input like x, and just notice the parentheses are on the wrong side of the function for historical reasons. And every function always goes at the beginning, so we don't write x plus y, we write plus xy. That's to avoid any kind of ambiguity. Okay, that's the notation. Now lambda calculus is just two simple things. The first thing is I get to make up new functions. So lambda just means I'm making a new function now. The first thing that happens is this is the input. I'm going to call the input to this function x. And the next part is what I do. I add x to itself. So this is a function that takes an input and adds it to itself. That's why I'm calling it double. I give it a name, the double function. Okay? Then the other thing I can do in lambda calculus is I can apply a function to an input. I apply double to 3. 3 plus 3 is 6, so I get 6. Okay, fairly simple. The magic of lambda calculus is that the inputs and outputs to functions can be other functions. This won't be too crucial for us today, but it's pretty neat. So for instance, a repeat function could be one that takes in a function, returns a new function that does f twice. In other words, that repeats it, right? So if we use that, we could repeat the double function, that gives us a quadruple function, apply that to 3 and get 12. So it's really remarkable that this system, lambda calculus, that just lets you make functions and apply functions to inputs is computationally universal, right? So that means that if what we want to start with is a language which can do any computer program, we can start with the lambda calculus. That's going to be enough. So that's where we want to start. The problem is it's deterministic. Okay? It does the same function every time. So every time you apply double to 3, you're going to get 6. There's nothing uncertain and nothing probabilistic in this so far. So what are we going to do? Well, it turns out that we can do something fairly simple. We can just add another primitive function to the language that does something random. So the function flip here, think of it as a function that flips a coin with a particular weight. So this is a coin that should come up heads 30% of the time. And it reports whether it's heads or tails. So maybe we flip that coin and we get heads, which I'm calling 1. And now A has the value 1. We do it again and B becomes 0. We do it again, we get 1 and C is 1. And then the last line says add up A plus B plus C. We get 2. Right? Now the critical thing here is that if we did the same thing again, we might get a different answer. We do it again and this time we get 0. Do it again and you get 1. Now imagine to yourself doing this over and over and over and over again, and then making a histogram. So just keep a tally of how many times you got 0, how many times you got 1, how many times you got 2. And you can make a plot like this, right? Maybe I got 1 more than I got 0, but I got 0 quite a bit more than I got 2, and so on. So on the right-hand side, what we have is a histogram, which is a representation of a probability distribution, the probability that we get 0, 1, and so on. Now we could actually go and do some math and compute that that probability distribution is some mathematical equation like this. The interesting insight for us today, though, is that we don't have to do that. So on the one hand, we have this standard mathematical notation that people use for probability. On the other hand, we have this notation where we just have these programs that make random choices. So I call that the sampling semantics and the distribution semantics. Sampling because we can sample a particular return value using this program. And there's a theorem, which is that these two things are actually equivalent. So anything that you can write down as a normal distribution in math, probability distribution in math, you can write down with one of these random programs, and vice versa. Any random program will give you a distribution. So that's great because it means we don't have to think about the standard mathematical notation for distributions, which, by the way, is good because those are hard to work with and very hard to compose together into compositional structures like we want. We can think just with programs. Now, programs are a classic case of a compositional structure. It's compositional because we take little pieces like the function flip and we combine them together into bigger and bigger pieces to make more and more complicated pieces of the random story, the story we're telling. Okay. Now, imagine that you have a program, so you've represented some knowledge as a little random process like this. Flip, 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 add them up, right? So usually what we want to do with probabilistic knowledge is not just write it down, I think the world works by these random choices. We also want to be able to ask questions. So these are usually called inferences or reasoning. And in church, I'll tell you why this is called, why there's church at the top of the slide in just a second. I gave it away by saying that. So in this language that we're constructing, we have a notation for asking questions. This is called conditional inference in the technical terminology. And the notation basically says, first I give you a set of definitions that specify some probabilistic knowledge. In this case, the knowledge is just that A, B, and C are each coin flips, each coin tosses with probability 30%. I then write down the query. This is the thing that I'm interested in getting the answer to. What's A plus B plus C? And then finally, I write down my assumption. So I write down, assuming that A plus B is equal to 1. So this says, what's A plus B plus C, assuming that A plus B is equal to 1? Okay, so let's dig in a little bit and try to understand how you could actually answer that hypothetical question, that query. So imagine doing the same thing that we did before. We go, we flip a coin, and we get 1, 0, 1. A plus B plus C is 2. But now we also evaluate this condition, this assumption, and we say, aha, that's true. A plus B is equal to 1. We do it again, 0, 0, 0. But now the assumption is false. So what we're going to do is we're just going to cross out that assumption and pretend that we never sampled that potential output value. Okay? We do it again. Uh-oh, the condition is false again. So we cross that out. We do it again. OK, the condition is true, so we can keep that one. And now if you make a histogram only of the things that are left, you're going to get something like this. This is called the conditional distribution. And remarkably, this is the right way to reason about A plus B plus C, assuming A plus B is 1, assuming the condition is true. So you could kind of redescribe this at a high level as reasoning is simply rejecting the impossible and tallying up whatever's left to figure out the plausibility of what remains. Okay? This is a way of redescribing the process that I just suggested to you. By the way, when I wrote that down on this slide, it reminded me of something. And I soon realized that it was this quote from Sherlock Holmes, from Sir Arthur Conan Doyle, which is, it is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. That's more or less what we're doing. We keep numbers around so that we can figure out, of those improbable things, how much more likely is one than another. But the key step here is excluding the things that violate our assumptions. One other thing. I said I'd get back to why does the top of this slide say church? It's not a religious statement. So the lambda calculus that this is based on was invented by a guy named Alonzo Church, that guy. And so this language that I'm working in is named after him. It's called the Church Probabilistic Programming Language. Okay, so all of that formalism is there to let us back up this basic idea of the probabilistic language of thought hypothesis, and it lets us give a much more formal and much more concise version. Really, we want to think of concepts, mental representations, as stochastic functions in a language like church. This is important for two reasons. It's important because they compose, you can stick two functions together to get a bigger function, and it's important because they support reasoning by conditioning, probabilistic inference, this operation that we just talked about where you get rid of the impossible things. Okay? One point that I want to make here before we go on is that the notation, the computational system that I just introduced you to, what's important is the representations that we give, the programs that we give, and the inferences that you're allowed to make from those representations by conditioning, by crossing out the impossible things. There are often much more efficient ways to actually exclude those impossible things than guessing and crossing it out, guessing and crossing it out. So you should think that all of the things I'm going to suggest to you are the inference that can be drawn, not necessarily the exact details of how you go about drawing that inference. Okay, good. So that was a bunch of very high level and technical stuff. Let's see an example. Let's see an example of using this to capture some, maybe if it had fit, I would have said moderately complex reasoning, slightly complex reasoning. So you all know, probably, hopefully, about the game of tug of war. Yeah? How many people have never played tug of war? Anybody? Ah, okay. Well, see me afterwards. I'll explain it. So tug of war is a game where you have two teams pulling on either side of the rope, and the stronger team pulls the weaker team over the line and wins. So if you just introspect about what's the set of concepts that you have in your head that lets you reason about a game of tug of war, you might come up with some concepts like this. First of all, there's strength, right? Each player has some raw ability to pull on the rope. But on the other hand, players don't always pull with their entire strength. There's some laziness that might happen from match to match or lack of effort. Strength and laziness only matter because there's pulling involved, right? There's pulling on this rope. In tug of war, it's not just one person pulling on either side. There are teams, so you have the concept of a team. And finally, and most importantly, there's a winner. Each match has a winner, so there's the concept of a winner. Okay, so what would it look like to try to take a very simple version of this set of concepts and translate them into church, into this notation that I just introduced? So you might first say, okay, I'm going to introduce a function. Remember, lambda introduces a function, which is strength. And that's a function where you give me a person, and I'll give you back a random real number, which in this case I'm just saying is a Gaussian. Gaussian is just some distribution over real numbers. So some people are stronger than other people. And there's an average strength. You can mostly ignore this little thing. This is here to make sure that every time I check somebody's strength, I get the same answer. So it's called memoization. But it's a technicality. Similarly, laziness is a function that takes a person and it randomly decides whether that person is lazy on a given game, on a given match. And I'm just arbitrarily saying they're going to be lazy on 10% of the matches. What about pulling? Well, the amount of pulling that a person does, I might just kind of encode the idea that they pull more when they're not lazy by saying, if the person is lazy, they pull with half their strength, strength over 2. And otherwise, they pull with their whole strength. Okay? What about the total pulling of the team? Well, here we first use a little function that says map. Map says apply pulling to every person who's on this team, and then take the sum of those things. So that just says add up how hard each person on the team is pulling. And finally, the winner. Well, the winner, I'm just going to say, the winner is the team that pulls the hardest. So if team 1 is pulling harder, they win, and if team 2 is pulling harder, then they win. Okay. So this is an incredibly kind of naive, simple-minded way of writing down these concepts. What I tried to do here was just capture some version of the basic set of concepts. The reason is because now we can do queries. We can do inference and ask questions. We can ask questions like this one. This one says, okay, here's my set of concepts. Here's my knowledge about tug of war. And here's some observations I have. Bob and Mary played against Tom and Sue, and Bob and Mary won. Bob and Bev played against Jane and Jim, and Bob and Bev won. And then I can ask you, how strong do you think Bob is? Right? I could change that. I could say, well, what if Bob and Mary were on the same team both times? Maybe you think that Bob is a little bit less strong then because it could have been Mary who's really strong. Right? And so you can see how there's going to be subtle patterns of evidence, subtle patterns of reasoning that emerge from just changing around the pattern of the evidence that I give you, and lots of different conclusions I can draw about lots of different people. One other thing I want to point out before I go on, because it's really easy to miss here, this set of definitions which give me the concepts for this domain, they never mentioned the particular names of people or the particular teams or the particular matches. Right? I don't introduce that until down here when I actually have particular evidence. And this is important because it means that this set of concepts can be applied to the infinitude of future tug-of-war matches that I might see. Admittedly, that's a fairly small infinity, but it could be unbounded, right? I don't know which tug-of-war matches I'm going to see in the future. Okay, so we did an experiment. What we wanted to see was how do people actually reason about this sort of situation. And so Toby Gerstenberg and I did an experiment where we gave people tournaments. We said it was ping pong instead of tug of war because that was easier for describing. And so we gave people a set of tournaments that were either singles or doubles tournaments, various players on the various teams, and then we put a wreath next to the team that won on each match. And then we would just ask people, we would choose a player and we'd say, okay, based on the results above, how strong do you think player VE is, from very weak to very strong? And people would adjust this slider. So what I'm showing you here is on the vertical axis is the model predictions. So each dot is one of the trials, the strength of one of the people, and I'm showing you the mean strength the model predicts versus the mean of the guesses that people make, right? So if the model is giving us exactly the numbers that the people give us in the experiment, then they should lie exactly on this light gray line, okay? They lie very, very, very close to that light gray line. The correlation here is 0.988. So what this says is that even that very simple model, which was very naive, is capturing most of the knowledge that people have to reason about the domain. Now, of course, there's other questions that I could ask that wouldn't be captured here, like, does player A get rope burn? Then I'd have to include concepts like ropes and friction. But for the set of questions that I can ask here about outcomes of matches and strength, this is able to capture people's judgments really, really accurately. We did the same thing now and said, well, let's just widen that a little bit. We already have this laziness concept floating around. What if people get evidence about that? So Toby came out with this dorky little sports narrator. And so after they saw the match, we'd have the narrator pop up and say something like, in game 2, player LS was lazy. And we told people ahead of time that laziness means you don't pull with your whole strength, just to make sure that was clear to subjects. And so now we can compare people's judgments where they integrate the outcomes of matches and this extra information about laziness with the model. And the prediction, again, is really good, right? So again, the model is able to integrate together this information about laziness and the outcomes of matches in a way that seems to match exactly how people are doing it, or very close to how people are doing it. What's the point of this kind of exercise? So this kind of exercise shows you how a very small set of concepts, just those 4 that we show, can lead to a huge, potentially infinite set of different inferences that people can draw. So this happens because we're using these random or stochastic functions which compose together and they support graded probabilistic inference. Right? So these 2 things that I said we were looking for in this overall theory. Now, that suggests that for a kind of toy domain, this little tug-of-war domain, we can do pretty good at capturing some knowledge that people have. But of course, people don't go around spending their whole lives reasoning about tug-of-war. They don't do it very often, to be honest, mostly when we ask them to. And so the next question that we want to address is whether we can start to capture things that are in some sense deeper and more central to everyday human cognition using the same set of tools. So here's a thought experiment. Actually, I'll show you the experimental data in a second, but for now it's a thought experiment. Imagine that you have a friend, Bob, and Bob has a favorite toy, which is this box. Now this box, you see when he brings it in one day, has 2 buttons on the top and a light. And now you see Bob playing with his toy, and he presses the 2 buttons and the light goes on. And the question is, how does the box work, right? So it could be that button A makes the light go on, and not button B. It could be that button B makes the light go on. It could be that either A or B would make the light go on. It could be that you need both A and B to make the light go on, or it could be that the buttons have nothing to do with the light. So just out of curiosity, how many people think that A or B alone could make the light go on? Okay, and how many people think that you need both A and B? Okay, so I would say of the hands, about 2/3 of the people think that you need A and B, and maybe 1/3 think that A or B is enough. Okay, so let me show you the experimental setup and the results. So it was exactly parallel to that story I just gave you, but we used several different situations and cover stories to make sure that it was the really core reasoning. So for instance, you work at a genetically engineered plants nursery, and one of your coworkers is tending to some almost dead flowers that you haven't seen before. Your coworker pours a yellow liquid and a blue liquid on the flowers. By the end of the day, the flowers are growing again. What causes the flowers to grow? We got subjects to respond to us by making bets. We said, here are the options, the yellow liquid or the blue liquid, the yellow liquid and the blue liquid, the yellow liquid only, etc. And we actually, in this case, had them make bets in the form of dividing up $100 amongst the different options here. We had a control condition. In the control condition, everything was the same, except we swapped out this middle paragraph for another version that didn't have an agent, a person in it at all. So a small earthquake knocks over a yellow liquid and a blue liquid, which pour on the flowers. Okay. And we did this in 9 different cover stories in 3 different domains: chemical, physical, biological. And so here are the results. In the condition where there's a person, so the social condition, people actually match what you guys did very closely. And I do this so often now that it works every time. It's quite striking. So people overall infer that you need both of the buttons A and B to make the light go on. If you take the person out of the situation and you just say, the earthquake did it, that goes away. Okay? People say, I don't know, it could be that you need A or B, it could be that you need A and B. People are a little bit less happy with the A alone and B alone for reasons we can discuss later. But the point is that you don't get this strong inference that it's the conjunction that's necessary. So this is really striking data because it tells us something, I think, really interesting about how people reason in this situation. And to see that, let's first set up a formal model that does very simple causal reasoning of the sort that you would try to do if you, for instance, had just read Karl Popper and were being a good scientist according to Popper's notions. So here's a structure where you say, okay, look, I think there's a true causal structure to the world, and given the actions, the button pressing, that gives rise directly to the events. And so my task is to do inference, to go from the actions and the events back to the true causal structure. There's many ways to set this up. One of them, which is just kind of using the notation I gave you a moment ago, says, look, there's some causal structure in the world that comes from some distribution of causal structures. It doesn't much matter what it is. There's actions that we just say come uniformly out of the blue. And then the outcome that I see comes from applying the causal structure to the actions that were taken, so the fact that somebody pressed the buttons. And then the important thing here is now we can do inference. We can say, okay, assuming that he pressed button A, pressed button B, and the light came on, what's the causal structure like? I'm sort of parroting a fairly standard causal learning model from the literature, Griffiths and Tenenbaum here. The interesting thing is that the different outcomes are all about equally probable under this model. Why is that? Well, this was confounded evidence, right? You saw 2 events at the same time followed by a 3rd event. That's confounded, and Karl Popper says you should wait I'm picking on Popper unfairly, but you should wait until you've deconfounded, you've seen only one of the buttons pressed before you can draw any strong conclusion, right? And so this causal only model makes very, very weak inferences, not what people did, right? So what we have to do to capture people's reasoning here, the first clue came to me from what people actually said in the first version of this experiment, which was, why else would Bob have pressed both of those buttons unless he thought he needed to? So we need to put Bob's beliefs in there somewhere. So we want a model that's more like this, where the actions don't just come out of the blue, but they're actually explained in terms of the beliefs and the desires and the decision-making of an agent. And again, we're then going to do inference. Okay. So what we need to do is capture this relationship between beliefs, desires, and actions. And one way that we can do it is by the idea of decision-making as probabilistic conditioning. So what does this little function that I just put up here say? It says, when a reasonably rational agent goes to make a decision, given the goal that they have, they do an inference. They say to themselves, what action should I take? So what's the action should I take, assuming that my goal is satisfied, given what will come from my action. So this assumption here says the goal should be true of what happens when I apply the causal model to the current state and my action. So that basically says, is my goal satisfied in the future? Okay. So using this kind of formalization of rational decision-making, take the action that will best achieve my goal, approximately. We can now make an extended model of causal reasoning. I'm calling this the social and causal combined model. And this is a model that, first of all, it explains where the actions come from. It says the actions come because that agent, given whatever his beliefs and goals are, decided to take those actions. It makes one other assumption, which is that the causal structure of the world and the causal structure that the agent believes are the same. I snuck this past you when I told you the story because I said it was Bob's favorite toy. That sets you up to think that he probably knows how it works. Okay, now the predictions of this model, if we do probabilistic inference over it, are much stronger. The predictions are that, in fact, it's much more likely that A and B are necessary to bring about the cause C. And the reason is basically that if only A or only B was necessary, Bob would probably have just pressed one or the other of them. Right? And so you would have been less likely to see this thing that actually happened. He pressed both A and B at the same time. And just to remind you, now, here's the experimental data, and here's those predictions from the social causal model, right? They're very similar. So it seems like in order to account for people's reasoning here they're directly just reasoning about the causal structure of this toy, but indirectly they must be reasoning about all of these mental things inside Bob, inside this other agent. Just in case you were worrying that this was some sort of artifact of having an agent there at all, we did another version that had a closer control condition where the agent was still there, but it was unintentional. So while reaching for a notebook, your coworker accidentally knocks over a yellow liquid and a blue liquid. There, if we split on whether people thought it was intentional or unintentional, we get the same effect. When they thought it was an intentional action, we get this strong enhancement of the conjunctive interpretation, and when it's unintentional, that goes away. Okay. So we just used this same formalism, these probabilistic programs, or the church language, to capture what's now a significantly more kind of real-world common sense kind of reasoning about causal structure and agency and the motivations of this guy who was playing with his toy. I want to move from there to something that takes a step towards even richer social cognition, which is a set of experiments on reference games. So a reference game goes like this. Here's the situation. There's two roles in this game, the speaker and the listener. And both the speaker and the listener know that this is the context or situation. So the speaker role goes like this. Imagine that you're talking to somebody and you want to refer to the middle object. You can either say blue or circle. You get to choose whether to say blue or circle. How many people will say blue? How many people will say circle? Almost everybody. Good. The listener is the exact opposite. So now imagine that somebody is trying to communicate one of these objects to you and uses the word blue to refer to one of these objects. which object are they talking about? So it's probably not this one because that's not actually blue. That's false. These are both blue, right? But how many people think that they're referring to this object? Couple. And how many people think they're referring to this one? Everybody else, right? Why? Well, if they wanted to talk about the one in the middle, they could say circle, right? For the one on the left, they don't have any particularly good way of saying it, so they might as well say blue. Right? And the fact that they say blue indicates that one, because if they had been wanting to talk about the other one, they would have said circle and so on. So how do we think about this formally? Well, we can use basically the same trick that we used a moment ago to think about Bob and his box. We start by having what we call the literal listener. And now the literal listener, oops, give you a sneak preview. The literal listener doesn't think about the other agent at all. They're using the literal meaning of these words. So they're in a situation with these three shapes, and they say, it's not that one, it could be either of those. And so when they have to choose one, they'll just choose one of those two at random. We capture that by saying, look, what they do is they infer one of the objects at random, assuming that the property is true of the object. So if you say blue, it should be blue. Okay. We'll come back to this prior, given the context, in just a second. Okay. Given that, we can make a model of the speaker. Now, the speaker maybe knows that this is how a silly listener is going to interpret what they say. And so the speaker says, what should I say? I'm going to think about how the listener works, realize that they're going to guess the right object if I say blue better than if I say red, even if it's not all that good, and so I'll go ahead and say blue. Right? So we capture that similarly by saying the speaker who wants to convey this object does an inference. What property should I use? Assuming that if the literal listener hears that property, they'll guess the correct object. Right? What should I say in order to get the listener to guess the thing that I want them to guess? It's basically what this says. Now we can go one more beyond that. We can make a model of the pragmatic listener, the smart listener. And the smart listener is a listener who's choosing an object by reasoning about the speaker who's reasoning about the listener. Right? So that looks almost the same. It says, look, I'm a listener who hears somebody say a particular property, blue. I want to infer what object they're talking about, assuming that if the speaker were trying to convey that object, they would have said that property. Right? That's my assumption. Now, each of these is very simple, but they go together into this fairly complicated nested reasoning process. Right? So I think that you think that I think that I'll choose blue. What's interesting is that this listener can draw much stronger inferences, right? Because they can think about what the speaker would have said if the speaker had intended to refer to the other objects, right? If this speaker had been trying to talk about different objects. So this model is all completely specified from this set of definitions, except for one piece, which is that this prior distribution over the objects, that's basically the probability that somebody would bother to talk about one object over another. In this context of objects, how likely is it that you would bother to talk about the square, the blue square? How likely is it you'd bother to talk about the blue circle, and so on? So we don't have any theoretical way to pin this down. Could depend on a lot of factors in the experiment. So what we're going to do instead is measure this experimentally and then plug it back into the model to make predictions for the speaker and the listener. So that experiment looks basically like the one that I started this section with. You say in the speaker condition are given a context of objects. There's a dotted box around the one that you're supposed to talk about, and you get to choose one of the properties. Similarly, the listener, you hear, for instance, the word dotted, and you have to choose one of the objects. Finally, in the prior condition, it's almost like the listener condition, but we say, imagine somebody's talking to you and uses a word you don't know to refer to one of the objects. Which object do you think it is? Right? So we basically just say, somebody's trying to communicate about something. What's your best guess about what that something is? That gives us this prior that we can plug into the model. We ran the experiment using all of the possible different sets of context that consists of three objects with two properties, say shape and color or shape and texture and so on. And we randomized whether it was shape or color or texture or which property we were actually using. And the results, so what I'm showing you is plugging in the results from the prior to make predictions about the speaker, empty dots, and the listener, the filled dots. The model predictions on the horizontal axis and the participants' judgments in our experiment on the vertical axis. And there's two important things to see here. The first is that people don't all say yes or no. This isn't a deterministic judgment. There's something about the context that can make this inference much stronger or weaker, and so there's a gradation from 0 up to 100 and a lot in between. And the second thing is that the model, this recursive I think that you think model, is able to capture how people make those judgments. Right? The model explains 98% of the variance in this data, has a correlation about 0.99. Just because you might have been wondering, yes, kids do this too. So my colleague Mike Frank and our student Alex Stiller and I ran exactly the same task using more kid-friendly stimuli. My friend has glasses. Can you find my friend? And what we see is that 3 and 4-year-olds and adults are all clearly above chance and better than a control condition where there's no label. 2-year-olds are maybe a little bit above chance, although it's very noisy. Okay. So this suggests that even 3-year-olds are able to do some kind of reasoning which captures this social context and takes into account what's called the pragmatic strengthening of these utterances, which is pretty neat. Okay, so I have 10 minutes or so left, I think. Okay, 15. So the last thing I want to look at, so signaling games, these games that we just looked at, they're very often used as a proxy for natural language. They're very much like our task in natural language where I have something to communicate to you and you have to guess it. They're a little bit more constrained though, right? In this case, we were just using a label and choosing an object. In natural language, there's much more unconstrained things. Something that I won't show you is the sort of immediate next step, which is extending that basic model that I showed you for reference games to handle simple natural language. You can just trust me, you can do that. You can extend it to something more like natural language, but still fairly straightforward. And it's in particular straightforward in the sense that the literal meaning of the words always has to be true, right? So when somebody said blue to me in the reference game situation, I would always choose a blue object. I might have a choice of which blue object to choose, and I might like to choose this one instead of this one, but it would always be blue. So that literalness property is not true of natural language in general. In natural language, we use lots and lots of kind of non-literal different ways to talk about the world that somehow manage to actually convey the right information. So imagine that you're reading a review on Yelp, which is this social recommendation site. I think it's more popular in the States than it is here. And you read a review of a restaurant that says, as I mentioned at the very beginning, it took 1 million hours to get seated. So the reviewer probably did not mean that literally, right? They probably didn't have that long to wait around and try to get seated. What they're trying to express instead is some sort of irritation, right? Not the literal value. So the puzzle for formal models of language understanding is why isn't this lying, right? So why is this something that we would call exaggeration or hyperbole as opposed to just a bad use of language, a lie? Another way to say it is, how is it that we can start in a conventional literal meaning but somehow use language in ways that are literally false? And by the way, literally these days often means figuratively, but I mean literally. Yes? Okay, here are the modeling ideas. It's getting a little bit late, so I'm going to tell you the basic ideas and just quickly show you the actual technical details. The ideas are two main ones. The first is that non-literal interpretation often conveys information not just about the actual verifiable world, but about the opinion of the speaker, right? Which goes beyond the objective state of the world. So one idea is, let's extend the world that we're using in these models to include not just the objective world, but also these affective, emotional, or opinion dimensions to the world. The second idea is that the speaker often has a goal of conveying information, but not arbitrary information. Sometimes the speaker just wants to convey his or her opinion about a particular thing in the world. And doesn't actually compare about the precise objective value in the world. So the idea there is to extend the model by allowing the listener to reason about what the speaker's goal was. What's the topic of this conversation? Is it how long did the guy actually wait? Or is it how he feels about how long he waited? Right? So just briefly, don't have to go through the details here, but we can do this pretty naturally in the sort of framework that I've been describing. So this smart, pragmatic listener now reasons about the goal of communication as well as the actual value communicated. The state space of the world has the actual number, S, as well as the affective opinion about the number, A. Goals could be the number, it could be the affect, it could be a noisy version of either of those if the guy only cared roughly what it was. And finally, there's one more assumption that we make, which is that round numbers like 100 are nicer and easier to say than unround numbers like 101. Okay, and I'll mention why we do that in a minute. Okay, so like before, we can't just directly go and compare this model to people's judgments because there's some background information that the model relies on. In particular, the model relies on some prior distribution about the number, how long do you typically wait for a seat at a restaurant, as well as probabilities about the affective opinion. So we measure those experimentally. We measure the distribution of price given category. How expensive do people think laptops are? How expensive do people think electric kettles are? How expensive do people think watches are? We also measure ahead of time the probability that somebody has a negative opinion given the category, a laptop, and the actual price paid. So how likely is it that somebody is annoyed if they paid $100 for a laptop? What if they paid $10,000 for a laptop? Okay. We plug those into the model to get predictions. And I'm going to show you just a summary of the model predictions here. So at the top, what I'm showing you is the 3 different categories that we used. This is the probability of an exact interpretation of the number. So that somebody says 50 and it actually means 50, that somebody says 51 and it actually means 51, and so on. This is the probability of an interpretation which is around the exact number, but not exactly the exact number. So the probability that they hear 50 and they interpret it as 51, or they hear 51 and interpret it as 50, and so on. This is the probability of a hyperbolic interpretation. So they hear 5,000 and they interpret it as 50, right, as much lower than the uttered price. I'll talk about this in a, well, okay. And this is the probability that they think the person was conveying affect, this opinion, by using that utterance. So the main things to notice about these predictions, first of all, they differ from one category to the other, which means that the model predicts that the background information you have about the category affects whether or not you'll interpret something as hyperbole and so on, right? So the background information affects the interpretation. That's a prediction. Another prediction, which is kind of subtle to see from this plot, but you see this sort of zigzag pattern here. This is called the halo effect. You're more likely to interpret a round number as approximate than vice versa. If you hear an exact number, you're more likely to interpret that as meaning exactly the exact number, according to the model. Okay, so how did we compare this to data? We did a very simple experiment. It looked like this. Eric bought a new electric kettle. A friend asked him, was it expensive? And Eric said, it cost $10,000. How likely is it that Eric thought the electric kettle was expensive? And the important data for the moment, for each of these prices, how likely is it that it actually cost that amount of money? Right, so 50, 51, etc. So we just had people give ratings from impossible to extremely likely. And so here's the aggregate comparison. The aggregate comparison, comparing the model to the human judgments, and each of the dots is a particular interpretation of a particular utterance. And again, the overall predictions are very good. So the model is overall able to predict how people will interpret these utterances. One important thing to notice about this, so the different shapes of marker are the different categories, and the fact that they all lie along the same line, as opposed to sort of different lines, means that the model is adequately taking into account the background knowledge people have about that category and correcting the interpretations to account for that, right? So that they all lie along the same line. The model and the human predictions match up. I think the other things I'll say in more detail in the comparison. So I want to give you some intuition for, do we actually need all of these things in the model in this case? So first of all, imagine you had a model that was not allowed to reason about the goals of the speaker. It just said, the goal of the speaker is to convey the actual price of the kettle, for instance. This is the utterance. So this is the example of how people interpret the utterance, the electric kettle cost $1,000. So if you don't have any goals, you have to interpret it literally. It costs $1,000. Right, good. Here's the human data. People obviously don't do that in this case. So that's a bad model. What if we allowed goals, but the only goal that we allowed was maybe he really means $1,000 and maybe he's being approximate. He just means around $1,000. So this is the model prediction if we do that. And sure enough, you see that, yeah, it could be that the guy meant $1,001, that he was being fuzzy. But it doesn't allow any probability that he meant a lot less than that he was being hyperbolic, right? And if you go look at the human data, there is this fuzziness between these two bars, but there's also this big bunch of responses where people say, no, actually, he only meant $50, right? So what if we allow the affect goal, that actually the speaker was trying to talk about his opinion about the matter, not the price? Well, there we get this effect, right? There we get this effect, this hyperbole effect, but we don't get the fuzziness effect. Of course, we can put them together, allow reasoning about the full space of goals, and then we match people's judgments quite well, right? So the complexity of this model really is justified, that we need to be able to reason about this full space of different potential communicative goals that the speaker had in order to capture when and how somebody is going to use number terms imprecisely. One more sort of model comparison, just to give you the flavor. We can look at the human data. This is the probability that somebody uses a hyperbolic utterance versus, probability that an utterance is interpreted as hyperbole, as an exaggeration, versus the utterance itself across the three categories. Importantly, it's different across the three categories. There are three different curves, and that's accounted for by the full model. But if we don't use the price priors, if we say, no, there's actually no background knowledge that we need here about the probability of different prices, then the model can't account for those differences, right? And so it does very badly. So we need to consider the space of goals, and we need to consider the background knowledge, how much people think an electric kettle versus a laptop is going to be. Final piece of data, and then we'll get to the end of this. The last question is, okay, not just how much did it cost, but how did he feel about that, right? So here we both said it cost $10,000, and we told them how much it actually costs, right? And then we said, okay, given how much he said and how much it actually costs, how is it that David thinks that the electric kettle was expensive? Here we get pretty good data, right? So this isn't as good a fit as I've shown you before. It's still, by the way, extremely good by psychology experiment standards. What's interesting about this data is that people only agree with each other with a correlation of about 0.83. Right? So basically, people have much noisier judgments about whether an opinion was conveyed, right? And the model is doing pretty well at capturing the data given that noisiness in people's judgments, right? It's fairly accurately able to decide, based on whether something is hyperbolic or literal and how hyperbolic it actually is, the extent to which people think that, oh, he's conveying a strong opinion here. So just to summarize this bit about language, I think this is really neat because non-literal language sort of resulted from understanding what the speaker cares about, and understanding what the speaker cares about allowed that pragmatic listener to discount the other information, the stuff that would have been literally false. It depends on common, uncertain background knowledge in a critical way. We've recently used the same framework for thinking about metaphors. John is a shark, that woman is a pistol, things like this. And I think in principle it can be used for lots of other really interesting non-literal language, but that's an ongoing direction. Okay, so what's the summary of what I've been telling you about tonight? The highest picture is a sort of partial potential answer to the question, what is thought? The big question. The idea is that these key properties of thinking, productivity and gradedness, can be explained from this probabilistic language of thought framework where we bring in probabilistic reasoning and compositionality as organizing principles. That can be realized in a precise way by using languages like Church, these probabilistic programming languages. And then we can use it as a kind of way of probing and understanding lots of interesting real-world high-level cognition, things like reasoning about other people's abilities, knowledge, language, and so on. And if this has got you interested, we have a book online that I use to teach my graduate class on this topic at probmods.org. Thanks.
Okay, thank you very much for your very interesting talk. So if you are like me, you have done a lot of complex reasoning during listening to this talk, and I'm sure there are lots of questions. If you want to ask a question, you can put up your hand and the microphone will come to you. And the first question is for John Herborn.
I knew what you were going to ask. I enjoyed your talk a lot, and I wanted to ask what your take is on all the commentary about how bad people are about probabilistic reasoning.
Yeah.
Right. That was full of examples in Kahneman's book, and it's been anecdotes for decades anyway.
Yeah.
So this is conjunctions they just don't get.
Yeah. No. This is a great kind of half empty, half full sort of case. So the blithe answer is just people are really good at a lot of the time, and then there are these corner cases where people fail. And I'm really interested in the things that people do well every day, all the time, and so I'm focusing on those. That's not the complete answer. So I think that's actually a reasonable answer. Kahneman and Tversky worked, and Kahneman describes this in his book. They worked very hard at a blackboard together to come up with corner cases where cognition seemed to fail, even though a lot of the time it works really well, right? And so in some sense, there's a difference of viewpoints between the kind of judgment and decision-making cognitive psychologist and the kind of computational modeling psychologist, of whether you're focused on the funny corner cases where people fail and mapping those out, or focused on the big bulk of things that are so obvious because people do them right? And I'm more interested in, as I'm obviously framing this, the big bulk of things. There's also a more subtle answer, which is that as you start to look at the phenomena that Kahneman and Tversky and others talk about, they're real phenomena, they're definitely there, but they're very heterogeneous. And many of them have explanations that are consistent with this sort of framework, right? It's illuminating to think about them, but consistent. So there's two things in particular. One, people are very, very bad at understanding probabilities when given verbally, okay? You'll notice that I tried, none of my experiments say it was probability 30% and assume that people will understand that, right? It uses qualitative sort of ways of communicating in language and ratings. That's important. Language just is not good at precise numbers in general and precise probabilities in particular. Another thing is that very often Kahneman and Tversky seem to have found ways and probed cases where the assumptions people bring to a problem mismatch the right assumptions for that particular problem in the modern world. And so you can sometimes explain those Kahneman and Tversky phenomena in terms of kind of not irrationality failures, but reasonableness given your assumptions. Right? This framework was all about formally and explicitly stating the assumptions. If they happen to be the wrong assumptions for the domain, too bad. Right? Finally, there are some cases where people are just bad. And in particular, as the scale of problems gets bigger, people get much less efficient at reasoning with them. And so there are cases where there's just processing difficulties. Right? But somehow the point of that is that there's a lot of heterogeneity in these phenomena, and rather than just summarizing it as people are bad at probabilities, I think it's much more productive to say people are remarkably good at inference, which can be described as probabilities a lot of the time, and then there's a diverse set of cases where people seem to be coming apart, and we need to look at those one at a time and see what they tell us about these sort of principles.
Okay. Just for the people who didn't get a reference to the book, it's about Daniel Kahneman's book, Thinking Fast and Slow, and it's very recommendable.
Very well written, yeah. So, I read it on the plane.
Next question.
Yeah, I have a question. Are bots sentient? Because I don't know which program language they use, but I have a friend on Facebook, and he's an AI dragon, artificial intelligent dragon, and you can talk to him to do the personality forge. I don't know which linguistics or programming language they use. You have always, you have also Brother Jerome, who is an advocate also on the forge for sentient bots. Well, are they these computer programs or these bots, are they sentient like humans, like we?
Yeah. So Searle, John Searle, challenged artificial intelligence with the Chinese room argument. He basically said, imagine you have a room that has a big book of rules, and the rules say, if these marks get passed in, do these things and then pass out these marks. And he imagined that the book was big enough and complex enough so that the things that you passed in were Chinese language questions, and the things that you passed out were reasonable Chinese language answers, and the person or people in the room didn't speak Chinese, they were just doing this right. So Searle used this to argue that AI systems should not be interpreted as sentient, because he said, clearly the room isn't sentient. I'm not so sure about that. I think you can argue that the room is sentient as a whole, and other people have. But I think basically the answer that you personally give to that question, is the room sentient, is very similar to the one that you're going to want to give to, are bots potentially sentient, right? Are the sort of things that you see and interact with on the internet. Could they, maybe they're not yet sufficiently, could they ever be sentient? I kind of think so, but...
Difference. You don't notice the difference. The only difference is the English language with advanced bots.
Yeah. You'll notice, by the way.
So you think it might be a human, even if you say I'm an artificial dragon.
Yeah.
Yes, he's my friend. He's one of my friends on Facebook. So.
Yeah. So I think it's interesting. Cognitive psychologists mostly try to avoid very hard talking about consciousness and sentience because it's a very hard question and it's unclear how to make progress with a lot of normal tools. There are some people who are doing interesting things in perception on consciousness. And frankly, for the purposes of the things that I was talking about and understanding how you could do common sense reasoning, I don't care very much if there's sentience. It would be nice to know that for other reasons, but I think it's sort of orthogonal to the basic question of how you could implement something to be intelligent.
So who else has a question?
Well, first of all, thank you for the nice talk. And so you basically use a set of probabilistic models that are very tailored to like a situation that you envisioned before, right? And then in that respect, it's not really that surprising that your models do so well at predicting this probability. However, to my mind, the most remarkable part of human mind is that it was not tailored for any of these cases, but actually it does very well in a whole set of situations that probably it has not encountered before. So the question is, how do these models help us to understand how such a sort of system manages to deal with situations that has not encountered before?
Mm-hmm. Good. So two answers to two separate, I guess, questions. One wasn't a question, but I think you maybe should be more surprised than you are actually surprised that these models fit the data that well. Because it's actually, these are things that have rarely been quantitatively studied and have never been quantitatively modeled for the most part, because it's actually very hard to come up with a coherent system that's going to give the right pattern of responses for these sort of things, where there's really quite a lot of data, quite a lot of patterns. So, if I made it look easy, that's great. I succeeded. But it's still somewhat surprising. Okay. But then you asked a question which is very close to my heart, which is, how is it that people can be so flexible, right? So I modeled one situation and then I modeled another situation. For people, all I had to do was tell them in the instructions for the experiment what they were supposed to do, right? So I didn't have to reprogram their mind. I just told them something. I programmed them by telling them something. And so I think that's the answer, right? Part of the reason that I've been studying natural language so much, and you sort of saw several of those here, is because I think our ability to understand natural language is part and parcel of our cognitive flexibility. The fact that you can just tell somebody, do this thing, and they can understand that. So how does this modeling framework help? Well, the model of language understanding that I sketched out here for you, it's a very general model of language understanding. It has separate components for what you do with words once you have their meaning and what the meaning is, right? So the meaning of words just essentially is a translation into something that builds a sentence which says yes or no, the literal meaning, right? And then there's this orthogonal component, which is how do you reason about the intended meaning? How do you actually do interpretation given that, right? So to the extent that that works, we now have a sort of program of, okay, let's write down the very general process of language understanding, and then let's gradually expand the set of words whose meanings we have sort of worked out. And as the set of words gets bigger, the set of sentences that you can construct out of those words grows not linearly, in the number of words, but exponentially, right? There's a combinatorial explosion. And so if you think of understanding a sentence as akin to interpreting a new situation, I think the way that we get the sort of flexibility that we're after is leveraging that combinatorial explosion, adding words one at a time, and then letting us handle not linear, but exponential number of different situations. That's the kind of, what I showed you here was up to where we are now, and that's the kind of 5 to 10 year imagination of how we're gonna make it go to that flexibility of human cognition. It's a good question.
More questions? Ben? So the microphone is coming to you. So Ben Meijering.
Some of the model predictions captured human data quite nicely. I was wondering about if you look at the inferences in terms of accuracy. People are good at making some inferences and bad in making others. Could you use, or let's say, how would you use your models to explain some biases that people have?
Accuracy in the sense of comparing the model to people's actual behavior, or comparing people's behavior to the truth in the world?
The second one.
Yeah, okay. Yeah, so this is interesting. This is related to the question about kind of Kahneman and those sort of things. And so, part of it is, so notice that in the sort of experiments that I talked about towards the end, they started to have this flavor where we said, look, if you have these beliefs, this knowledge about what the world is like, this prior distribution for different categories, then this is the interpretation you should draw, this is the reasoning you should do, right? So what it was doing was connecting the beliefs that people had about, say, the domain, right, to how they interpret language for that domain. Now, there's nothing in there that said that people's beliefs about the domain was right, right? So one way that you can get biases is if people have background knowledge which happens not to be right, they'll use it reasonably and draw the wrong conclusions because their initial knowledge was wrong, right? And you can get incorrect background knowledge from people tell you the wrong things, you observe the wrong things, all sorts of sources. So one source of that sort of bias is simply your knowledge is wrong. Your beliefs about the world, you're doing the right thing with them, but your beliefs aren't actually the way the world works in one way or the other. The other main way, which I sort of alluded to earlier, is so systems like the one that I showed you, church, they have to do these inferences somehow. And it's very useful and easy to understand them as crossing off the ones that aren't false, but that's not a very efficient way to do it, right? There are lots of other ways to do this, lots of other algorithmic processes. And many of those algorithms get very close to the correct inference, conditional probability answer for small situations. As the situations get bigger, they can start to diverge. And so I think another source of bias is people's algorithms sometimes are not actually approximating the sort of predicted answer all that well, right? Not so much in the experiments I showed you. Those were chosen to, in general, be situations that were sort of cognitively tractable. But in the real world, this happens. So those are two kinds of things that I'm on the lookout for when I think about sort of errors that people make.
Okay. More questions? And then I also have a question. Could you go back to the slide that says kids can do this too, with the glasses? Yeah, so it seems that in that case, children who are very young can already do it remarkably well. And you can compare that maybe to the false belief task that they can only do when they are 4 years old. So kids of 4 years old can only reason about, for example, that their mother doesn't know something which they themselves do know. And I was wondering how you could explain that. Aren't they doing a different task here?
Yeah, so there's a backstory to why we bothered to do this, why this was interesting, which is that until recently, people thought that kids couldn't do pragmatic reasoning until they were 7, right? More or less, till they were quite old. So there are other tasks that have a very similar structure that are called scalar implicature, So, for instance, some of my friends have glasses implies that not all of my friends have glasses. And that's kind of isomorphic to this. You can see glasses like some and hat like all. So some implies not all is like saying glasses means the middle guy. And kids are terrible at that sort of task, at that sort of scalar implicature task. So one interpretation is kids just can't do pragmatics. They don't, they haven't learned it. It has to come online, something like this. Another interpretation is that actually kids are fine at pragmatics itself, but there's some part of the pragmatic process that causes difficulties, right? So that young kids just can't kind of get it in time. And several people over the last, 5 years have started saying this and thinking this. And so our thought was, well, maybe kids are pretty good at the basic idea of pragmatics, but they need the alternatives to be really explicit, right? So in the scalar implicature with quantifiers, the alternative utterance, I say, some of my friends, blah, 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 and you have to be able to conjure to mind that there's an alternative which is all and reason O. They didn't say the alternative all. Here, the alternatives, there's the same alternative process, but the alternatives are much more immediate, right? Glasses, oh yeah, there's a hat there. He could have said hat, right? And so our thought was, well, maybe in this kind of what's called ad hoc implicature task, kids will be better at it because the alternatives are so much more salient. They're just right there, right? And so, sure enough, kids are better at it. And our interpretation is that it's the explicitness of the context. There's a piece of converging evidence from Dave Barner's lab. He did an experiment where he was doing quantifiers, the scalar implicature, but he very, very strongly primed kids to know that all was an alternative. He sort of did a little task initially where they talked about all. And in that case, he starts to get successes at the standard scalar implicature with much younger kids. 4-year-olds definitely, and I think 3-year-olds, although I'm not sure. So it seems like what's actually going on here is that the competence of pragmatics is there, but the sort of processing demands of bringing the alternatives in fast enough to incorporate them are beyond the reach of the little kids, right? So in some sense, it's maybe one of these complex working memory or activation stories that seems to be in play.
But in this case, could it be that they are not really reasoning about the speaker, but that they simply prefer the pictures in which only one thing is salient?
No, we control for that. Yeah, we have, so the light gray bars are a control condition where there's no label but the same set of objects, and those are down there, yeah.
Thanks. Okay, any more questions? Well, in that case, we would like to thank Noah Goodman again for the very interesting talk and questions.